Well, hello, dear Cardano community, for the report about the Catalyst 5 grant that we at Moon have received. Our goal was to start employing formal methods to ensure the safety of smart contracts deployed in our language Glow. As you know, when a smart contract is deployed, it cannot really be updated, so this leads to a situation where bugs, including safety holes, are visible to everyone without being easily fixable. Those high stakes involved in developing dApps can discourage programmers from developing them, so this hurts the whole ecosystem. We used a cost-benefit analysis to identify the features that would let us quickly get a working implementation that we can safely build on. In other words, we built a tool to investigate the properties of a dApp or smart contract as a whole. At the same time, we began an organized effort to facilitate community involvement in design and feedback. The development of our prototype let us successfully see that a Glow program can be augmented by integrating existing tools and theories from the world of formal verification. Also, we now know that this maneuver extends the range of expressible properties of smart contracts in an adversarial environment. And now I have the privilege to leave you with Alex Plotnik, our CTO, for the technical part.
Here we have a Glow contract for a simple game between two players, A and B. First, each player deposits one token into the contract account. This is their bet, to be held in escrow until the end of the game. Then each player chooses a Boolean value that is true or false and publishes it on the chain. A chooses first, then B. Finally, we compare those two choices to determine a winner. If the two values are the same, we say that A wins. The statement labeled A takes all withdraws the two tokens to A's account. If the values are different, then B wins, and they get to withdraw the tokens. In this demo, we're not going to play the game. Instead, we're going to try to determine whether or not the game as written is fair, that neither player can control the outcome of the game. What we'll see is that the way this contract is currently written, it is not fair, and that with a little help, Glow can prove that it isn't. First, we'll run the formal verification pass on the unmodified contract. This doesn't produce any errors or warnings, so it's a syntactically correct Glow program with no type errors. To prove the game theoretic properties of the program, we'll use the new assert construct to reason about the program itself. We'll start from A's perspective, and what we'll try to prove is that A can intentionally cause execution to always reach the A takes all statement. That is, they can force the game to come out in their favor. So we'll ask Glow to prove this, again using the formal verification pass of the Glow compiler, and it comes back with no. It has disproven this assertion because in fact A cannot force the game to come out in their favor. Let's see if they can intentionally throw the game, that is, to force it to come out in B's favor. Nope, they can't do that either. Okay, now let's switch to B's perspective and try to verify the same two assertions. The first is that B can force A to win, that is, to reach the A takes all statement. And the verification of this assertion succeeds. Let's check the next one. Can B always win? That is, can they always reach the B takes all statement? Yes, indeed they can. Now, the reason for this is that A is publishing their choice before B makes theirs. This means that B gets to incorporate that knowledge into their own choice, so they can completely control the outcome of the critical test. So this is a semantic bug in the way the game was encoded, and the Glow formal verification system was able to expose the bug before it was too late.